On the north coast of Alaska, behind a house, under a plywood shed that looks like it was built to store a snow machine, there is a hatch in the floor. Lift it, and you are looking at a ladder. The ladder goes straight down into the ground, past the mud and the gravel, past the layer that thaws every summer into something older and harder, and then it opens into a room. The room is not a basement. Nobody poured a wall. Nobody plugged anything in. It was cut out of frozen earth with hand tools and patience, and the walls are the earth, and the ceiling is the earth, and the floor is the earth, and every one of those surfaces is below freezing all year long. 20-some feet down, the air holds steady in the low 20s Fahrenheit through July, through August, through a week in June, when the tundra above is soft and green, and mosquitoes come off the ponds in clouds. Meat hung on a hook down there in April is still good in December. The Inupiaq word is sigluak. In English, people usually say ice cellar, and that is close enough, though it undersells the thing. It's a refrigerator with no compressor, no coolant, no wiring, no repair bill, and no failure mode anyone had ever needed to plan for. It runs on the single fact that the ground on the Arctic coastal plain is frozen, and stays frozen, and has stayed frozen for longer than any story anybody tells about it. Communities along this coast have been building them for at least 1,000 years. That is not a figure of speech. Researchers who study these structures put the practice back at least a millennium, based on variable designs across a long stretch of coast, and the practice was still fully alive in the 21st century. A whaling crew lands a bowhead in the spring. And a bowhead is not a deer. It is tons of food, and it belongs to the whole community, and it has to be kept somewhere cold enough and dry enough and big enough to hold it while it is shared out over the months that follow. Electric freezers can be bought, but running enough of them to hold a season's harvest is expensive in a place where power is expensive, and the taste is wrong. Meat aged underground is what people prefer. There's also a food safety argument in favor of the cellar that gets less attention than it deserves, because storing that much meat in sealed containers carries a botulism risk that an open, cold, ventilated chamber in the ground does not. So the cellar counts as infrastructure, in the plainest sense of that word, and it works because of a physical assumption nobody ever had to write down, because nobody ever had reason to doubt it. Then something turned this into a different kind of story. In 2005, a monitoring network was set up in the town then called Barrow and now officially called Utqiagvik, the northernmost community in the United States. The work was done through a long-running program that tracks the seasonal thaw layer across the Arctic in cooperation with local whaling captains and with the native village of Barrow Inupiat traditional government. 5 cellars were instrumented. Small temperature loggers were strapped to support beams and tucked behind ladders, out of the way, where they'd take a reading every hour or every 2 hours, year in and year out. Once a summer, in August, somebody would climb down and pull the data. 14 years of that. Glamorous it is not. A wall of numbers about the air temperature inside 5 holes in the ground. Read it straight through and it tells you something that is easy to state and hard to absorb. All 5 cellars stayed below freezing the whole time. That part is real and worth saying clearly, because the story that gets told loosely is that the cellars are melting, and that isn't quite what the instruments say. Warmest daily readings across the 5 ran somewhere between about 24 and 26 degrees Fahrenheit. Coldest daily readings ran down to somewhere between about 12 degrees and about 2.5 degrees. Cold rooms, functioning rooms. And yet, of the 5 cellars in that network, 2 flooded. Another was abandoned because its walls were sloughing inward. The remaining 2 were still in use right up until the pandemic, and when researchers came back and went down into them in August of 2022, neither one was in use anymore, both having taken on water during the quarantine period when nobody could get in to maintain them. 3 of the 5 showed mean annual internal temperatures trending upward across the record. The other 2 held steady in temperature and flooded anyway. That last detail is the one I keep coming back to because it breaks the simple version of the story. If this were only about warmth, the cellars that stayed cold would have stayed fine. They didn't. The people who ran that monitoring program said so plainly in their published conclusions, the failures were not driven purely by some thermal line being crossed. They came out of an interaction, warming conditions on one side and human activity on the other, together chewing away at the mechanical integrity of the structures. That shape, warming on one side, human activity on the other, neither of them sufficient alone, is going to describe almost everything else on this coast. There was a survey done in 2012 that went around and located every ice cellar anybody could point to in Utqiagvik. 71 of them. Some in sheds, some out in the open, some deep, some shallow, some in daily use, some already given up on. Cellars along the shore in the older part of town, the neighborhood people still call Barrow, had already been lost to the sea, and others sit close enough to the edge that sandbags have been stacked along the Chukchi shore to buy them time. The failures themselves are almost mundane when you look at them one by one. One cellar took on water catastrophically in the spring of 2010, and that was the end of its data record and the end of the cellar. One of the deepest, a little over 20 feet down, developed bowed walls in the wooden-lined entrance shaft, bowing that had already started before the loggers went in, and the deformation kept going until climbing down there became a genuine safety question. One cellar filled up with weasels, which sounds funny and is not, because a chamber that animals are getting into is a chamber you cannot trust with a season's food. One had its data loggers pulled out and misplaced during a clean-out. None of that reads like catastrophe. It reads like maintenance. It reads like an old house. That is exactly why it's the right place to start. Because a refrigerator made out of the ground only fails if the ground changes. And the ground changing is a much larger event than the loss of a room. Every cellar on that coast is a small, private, decades-long experiment in whether the frozen earth of northern Alaska will keep doing what it has been doing. The people running the experiment did not design it as an experiment. They dug the holes to keep food. But they were functionally the first instrument network on this landscape, and they were reading it correctly and saying so out loud years before the science caught up. That's documented too. As early as the 1970s, researchers recording community observations in Utqiagvik and other Arctic communities were being told about changes in the frequency and intensity of storms, about sea ice getting thinner, and about the taste and appearance of meat stored in cellars going wrong. Those weren't hunches. They were the observations of people whose lives depend on reading this specific ground, delivered decades before the borehole record and the satellite record were mature enough to argue about it. There's a framing trap in this material, and it's worth naming before we go further. It would be easy to turn this into a story about hardship, about a way of life under siege, about people being acted upon. That framing is both condescending and inaccurate. Utqiagvik is a working city of roughly 5,000 people, a majority of them Inupiat, and it is the seat of a borough that runs schools and a search and rescue operation and a wildlife management department that has done serious, respected science on bowhead whales for decades. This is not a community waiting for someone to explain its own coastline to it. When the cellars started failing, people responded the way anyone responds to a failing appliance. They diagnosed it, they argued about causes, they tried fixes, and some of the fixes they landed on are strange and clever. The question the cellars raise is simpler and bigger than any single fix, though, and it is the question this whole story runs on. If the ground under a town is an appliance, and functionally, on the North Slope, it is, It holds up buildings. It holds up roads. It holds up runways. It holds the sides of a hole open so you can hang a whale in it. Then what happens when the appliance changes state? Not disappears, not melts into soup, changes state at the edges unevenly, in places nobody was watching, on a schedule nobody set. And there's a second question stacked underneath the first, and it is the one that turns this from a regional story into something with a much longer reach. Nobody put that ground there for our convenience. It has been accumulating for a very long time, and it has been accumulating things. There is material locked in the frozen part of the Arctic coastal plain that has not been in contact with the open air since before the last ice age ended. Some of it is ice. Some of it is peat and old plant matter, and the remains of tundra that lived and died and never fully rotted because the cold shut the process down partway through. And some of it, in the last 80 years, we put there ourselves. That is the shape of what follows. A hole in the ground behind a house in Utqiagvik that keeps meat cold is the visible end of a system that runs several thousand feet down, several hundred miles inland, and about 80 years back through the industrial history of the United States. The cellar is the clue. The system is the case. So let's go down the ladder properly and find out what this ground actually is. Start with a word that gets used loosely. Permafrost is not ice. It's a temperature condition. The definition is boring on purpose. Ground that stays at or below freezing for at least 2 consecutive years. That's it. It doesn't specify what the ground is made of. Permafrost can be frozen gravel, frozen sand, frozen silt, frozen peat, frozen bedrock. It can be bone dry. In parts of Antarctica, there's permafrost with almost no ice in it at all. And if you thawed it out, nothing would happen. It would just be dirt that got warmer. That is not the situation on the North Slope, not remotely. On the Arctic coastal plain of northern Alaska, the ground is loaded with ice, and it is loaded with ice in several distinct forms that behave in completely different ways, which turns out to matter a great deal for what happens when the temperature comes up. There's pore ice, which is water frozen in the spaces between grains of sediment, the way ice fills a slushy. There's segregated ice, which forms as lenses and layers when water migrates toward a freezing front over long periods and builds up in sheets, sometimes sheets thick enough to see clearly in a cut bank. And then there are ice wedges, which are the ones that give this landscape its face. Ice wedges start with a crack. In deep winter, when the ground gets extremely cold, it contracts and it splits. A thermal contraction crack, a hairline fissure running down into the frozen soil. In spring, meltwater trickles into that crack and refreezes down there, where it's still cold. Now there's a thin vein of pure ice in the ground. Next winter, that vein is the weakest line in the soil, so the ground cracks there again. And more meltwater goes in, and more ice freezes. Do that for a few hundred years, and you get a wedge of clean ice wide at the top, tapering downward, sometimes several yards across at the surface, and running down many feet. Do that across an entire coastal plain, and the wedges connect into a net. That's why the tundra up there, seen from any height, is covered in polygons. It looks tiled. It looks like the ground was scored by something with a plan. On the coast near Drew Point, where this has been mapped in detail, those polygons run from about 20 feet to about 80 feet across, with a typical one somewhere around 50. The rims and troughs are the surface expression of ice wedges standing in the soil like the walls of a honeycomb, and they are pure ice, and they are load-bearing. Now put a number on how much of that ground is ice. Along the coastal bluffs near Drew Point, the total volumetric ice content of the frozen material runs roughly 80 to 90%. 8 or 9 parts in 10 by volume is ice. In some of those bluffs, the segregated ice alone accounts for well over half the volume, and wedge ice can make up something like a third in places. That number is the single most important physical fact in this entire story, and almost nothing else makes sense without it. That ground is not soil with some ice in it. It is ice with some soil in it, which means that when it warms past freezing, it doesn't just get soft, it loses volume. The ice becomes water, the water drains or pools, and the ground surface drops. That process has a name: thermokarst. And it works differently from ordinary erosion, where material gets picked up and carried somewhere else. This is collapse. The land falls into the space its own ice used to occupy. Now, how deep does this go? Under Utqiagvik, the permafrost is continuous, and it is more than 1,000 feet thick. At 50 feet down, well below anything the seasons can reach, the ground sits at roughly 16 degrees Fahrenheit, 16 above zero, year-round forever. As far as any living person's experience goes, move east along the coast to the Prudhoe Bay area and it gets deeper. Ice-bearing permafrost there has been measured at something over 2,000 feet thick. Head inland toward the foothills of the Brooks Range, and it thins out, generally down into the range of 600 to 1,300 feet, because the geology changes and the ground surface runs warmer the farther you get from the coast. 2,000 feet of frozen ground. At that scale, you have stopped describing a soil horizon and started describing a geological unit. And it did not form recently. Permafrost that thick is the product of an extremely long cold period, built up over glacial cycles, thickening from the top down over tens of thousands of years, and in the deepest sections far longer than that. The material inside it is correspondingly old. On the coast near Drew Point, where researchers have gone into the bluffs and dated what's in them, the upper layers, the organic rich soils and old lake sediments in roughly the top 10 feet, carry radiocarbon ages running back on the order of 12,000 years to the tail end of the last ice age. Below that, in the Pleistocene marine sediments that make up the lower bluff, the dated material comes in around 37,000 to 47,000 years before present, with some evidence that it was reworked before it got there. So when a chunk of that bluff comes off into the Beaufort Sea, what enters the water is material that has been out of circulation since roughly the time the last Neanderthals were alive. It's worth asking how ground gets to be 2,000 feet frozen, because the answer explains something about where the North Slope sits in deep time, and it sets up a wrinkle offshore that most people never hear about. Permafrost thickens from the top down. Cold at the surface propagates into the ground. Heat from the Earth's interior pushes back up from below, and the thickness of the frozen layer settles at whatever depth those two effects balance. Warm the surface, and the frozen layer thins from the bottom, slowly, over centuries and millennia, as geothermal heat wins back territory. 2,000 feet of it means the surface was very cold for a very long time. During the glacial periods of the last few 100,000 years, northern Alaska was cold, dry, and, this surprises people, largely unglaciated. The Brooks Range carried glaciers, but the coastal plain to its north was not buried under a continental ice sheet the way most of Canada was. It was open ground, cold steppe, grazed by mammoth and steppe bison and horse, dusty with wind-blown silt, with the freezing front driving deeper and deeper into it century after century, which means this permafrost was never sheltered beneath an ice sheet at all. It came straight out of tens of thousands of years of extreme surface cold acting on exposed land. And that has an odd consequence, because a glacier is actually an insulator. Ground under a thick ice sheet can be warmer than ground exposed to an Arctic winter sky. The North Slope got the full cold, unprotected, for a very long time. Sea level was also far lower then, enough water locked up in ice sheets that the Bering Land Bridge was dry ground, and you could walk from Alaska to Siberia. The continental shelf that is now under the Beaufort and Chukchi seas was exposed plain, continuous with the coastal plain. And it froze the same way for the same reasons. Then the Ice Age ended, and the sea came back over it. The permafrost that formed on that shelf did not vanish when the ocean returned. It was submerged. There is relict permafrost beneath the seafloor off northern Alaska, frozen ground that formed on dry land and has spent the last several thousand years underwater, being slowly degraded from above by seawater that never drops below about 28 degrees Fahrenheit. It's been mapped in places by seismic surveys and encountered directly by drilling associated with offshore development. There is ground under the Beaufort Sea that is frozen because it used to be a plain that mammoths walked on, and it has been thawing continuously since before the pyramids, and it will keep thawing for thousands of years, regardless of anything anyone does, because it is a leftover from a world that no longer exists. That's the honest, deep-time context for everything else in this story. The permafrost of the North Slope is already in a long, slow retreat that started when the last ice age ended. Terrestrial permafrost across the Arctic has been thinning from the bottom throughout the Holocene. That process has nothing to do with the last century, and everything to do with the fact that the last 10,000 years have been much warmer than the 10,000 before them. What the last century did was add a second signal at the other end of the column, moving in the other direction. A warming pulse entering from the top, propagating downward, and reaching the depths where things are anchored. That's the difference that matters. The slow thinning from below is thousands of feet down and irrelevant to anything anyone built. The warming from above is in the top 30 feet, which is where every piling, every gravel pad, every ice wedge, every cellar, and every well casing lives. There's one more thing to say about depth before we come back up to the surface. Everything that matters practically about permafrost happens in a very thin skin at the top of an extremely thick body. That's a hard thing to hold in mind because the numbers are so lopsided. 2,000 feet of frozen ground, and the consequential zone is the top 1 or 2% of it. If the permafrost under Prudhoe Bay were a 5-story building, the part of it that determines whether a road stays flat would be the paint, which is why arguments about whether the permafrost is disappearing mostly miss the point. It isn't. It doesn't need to. A layer thin enough to measure in inches, thawing a little deeper and refreezing a little later, is entirely sufficient to bend a pipeline support, flood a cellar, tilt a building, close a road, and let the sea into a bluff. Between that deep frozen mass and the open air, there's one thin, busy layer, and everything human happens inside it. It's called the active layer. It's the part of the ground that thaws each summer and refreezes each winter. On the North Slope, it is startlingly shallow. Across 20 long-term monitoring sites on the slope, a Forestwallman study Montani, the average maximum thaw depth in 2016 came in at about 20 inches. And that was the deepest average in 21 years of measurement, roughly an inch and a half above the long-run average for the period. Right around Utqiagvik, more recent measurements have run in the range of 13 to 17 inches, somewhere between 1 foot and 2 feet. That's the whole living surface. Below that, permanently frozen, for a third of a mile. There's a complication buried in those thaw depth measurements that took researchers a while to account for, and it's a good example of how easy it is to underread this landscape. Thaw depth is measured downward from the ground surface, but on ice-rich ground the surface itself is dropping, because when ice in the upper permafrost melts, the material above it settles into the space. At monitoring plots around Utqiagvik, that settlement was tracked across the years 2003 to 2015 and came out somewhere in the range of 1/6 of an inch to 4/10 of an inch per year, adding up to a net loss of ground elevation on the order of 3 to 6 inches over that period, which means a probe pushed down from a surface that has sunk 4 inches and stopped at the same reading as last year has not found the same thaw depth. It has found a deeper one, measured from a lower starting point. The ruler and the thing being measured are both moving in the same direction, and if you don't correct for it, the ground looks more stable than it is. 3 to 6 inches over a dozen years is not a dramatic figure. Nobody standing on that tundra would notice it. But spread it unevenly across a landscape, more where the ice is concentrated, less where it isn't, and you get exactly what the coastal plain has been doing. Troughs deepening, ponds appearing, drainage rerouting, and a surface that no longer sits where the survey said it did. Everything that grows up there roots in that shallow, soggy, imperfectly drained layer. Water can't sink out the bottom because the bottom is frozen and impermeable, which is why a landscape that gets less precipitation than parts of the American Southwest is covered in ponds. The tundra is wet, not because water falls on it, but because water can't leave. And the vegetation on top isn't decoration. It's insulation. A mat of moss, sedge, and peat is a startlingly good thermal blanket, and it is one of the main reasons the permafrost underneath survives summers that go above 60 degrees Fahrenheit. Strip that mat off, and the ground beneath it warms, and the active layer deepens, and the ice starts to go. That is the single most important practical rule of engineering in the Arctic. And the North Slope has an unusually vivid demonstration of what happens when you ignore it. First, the thermal state itself, because this is where the record stops being ambiguous. The United States Geological Survey has been putting thermometers down deep holes in northern Alaska since the late 1940s. That's an unusually long instrument record for anything, let alone for ground temperature in a place that's hard to reach. And it produces a particular kind of evidence that I find genuinely beautiful in a nerdy way. Here's why. Deep ground is a slow, honest recorder. Heat moves through frozen sediment by conduction, and conduction is sluggish, so a change in the temperature at the surface takes years to decades to show up at depth. A borehole temperature profile, the curve of temperature against depth, should in a stable climate be a nice straight line, getting warmer as you go down because of heat coming up from the Earth's interior. If the surface has been warming, that line bends near the top. The size of the bend tells you how much warming, and the depth to which it has propagated tells you roughly how long ago it started. When researchers read those profiles from northern Alaska, the bend was there. The permafrost in the region had warmed, typically by 2 to 4 degrees Celsius, call it 4 to 7 degrees Fahrenheit, and the depth the signal had reached indicated the warming had begun something like 40 to 80 years earlier. Some holes showed little change, and a few showed cooling, which is exactly what an honest dataset looks like. But the regional signal was unambiguous, and it was recorded by rock and ice, passively, for decades, without anyone asking it to. The ground had been keeping notes. What's happened since is more direct, because since the late 1980s, there have been permafrost observatories on the slope taking readings every year at fixed depths. At 65 feet down, deep enough that seasonal swings are gone and you're reading the multi-year trend cleanly. North Slope sites have been warming since 2000 at rates between roughly 0.2 and 0.7 degrees Celsius per decade. Which test always, which is somewhere around half a degree to a degree and a quarter Fahrenheit every 10 years. In 2016, every permafrost observatory on the North Slope except one hit a record high at that depth. At Deadhorse, the industrial settlement at Prudhoe Bay, the numbers are blunter. The mean annual ground temperature at that research site was measured at about 17.5 degrees Fahrenheit in 1988. By the mid-2010s, it was running around 28.5. Freezing is 32. Now that figure describes the temperature at the top of the permafrost at one instrumented site, not the whole column and not the whole region, and the deep permafrost under Prudhoe Bay is in no danger of vanishing in any human time frame. 2,000 feet of frozen ground does not go anywhere quickly, but for anything built on the surface, the number that matters lives in the top 30 feet. And in the top 30 feet at Deadhorse, the margin between the ground's condition and the phase change that ruins it has narrowed from about 15 degrees to about 3.5. Margin is the whole game here. Frozen silt is a competent foundation material, better than its reputation, stiffer than a lot of what people build on in the lower 48. Thawed silt with the ice taken out of it is mud. There is no gentle intermediate. The transition between those two states happens over a couple of degrees, and once you're inside that couple of degrees, everything else about the design stops mattering as much as the temperature does. Around Utqiagvik, the same story shows up in a different set of numbers. Mean annual air temperature over the town rose steeply across the years the cellars were being monitored. In the undisturbed tundra outside the community, mean annual air temperatures have gone up by something like 5 degrees Fahrenheit over the longer record, and the ground 50 feet down has responded by warming about 2 degrees. 2 degrees at 50 feet is a lot. Weather doesn't reach 50 feet down. That figure is the whole thermal regime shifting. And there is a small, almost comic episode from 2017 that says something about how fast this has moved. Utqiagvik's climate data got automatically flagged and pulled from certain national data products, not because the station was broken, but because the warming trend was so steep that the quality control algorithm concluded the readings had to be in error. The software had been built with an assumption inside it about how much a place can plausibly change. The place changed more than that. I like that story because it's the same failure as the ice cellar, at a completely different scale. Something built on the assumption that the Arctic is stable, quietly not working, and nobody noticing until the thing itself refuses to run. So, the ground is immensely deep. It is loaded with ice. Its surface layer is thin and thawing a bit deeper, and its temperature has been climbing for decades in a record that goes back to the 1940s. Now the important part, what does that actually look like on the ground day to day for someone standing on it? Mostly, nothing. That's the strange thing. Permafrost thaw is not a spectacle. There's no roar, no crevasse, no dramatic collapse across a valley. Most of the time, the tundra in northern Alaska looks like the tundra in northern Alaska. Flat, wet, brown and gold and green, depending on the month, hazed with insects in July. Absolutely silent in a way that people who've spent time up there describe as physical. What changes is subtle and cumulative and shows up in the shape of the surface. Where ice wedges start to melt at their tops, the ground above them settles, and the troughs between polygons deepen. Water that used to spread out across the tundra now runs into those troughs instead. And standing water is dark, and dark surfaces absorb more summer sun than pale ones, and absorbed heat melts more of the wedge. That's a feedback, and it's a well-documented one across the Arctic. The polygon net starts to stand out more sharply. Ponds appear along the lines, where a lake drains, and lakes on the coastal plain do drain, sometimes catastrophically. When a channel cuts through to a lower one, the exposed bed can thaw and settle. Where a slope is steep enough and ice-rich enough, thawing at the surface can start a retrogressive thaw slump, which is one of the few permafrost features that puts on a show, a head wall of exposed ice melting back into a hillside, the thawed material sliding away below it, the whole feature eating backward through the slope for years at a time. Add these up across a coastal plain, and you get a landscape that is quietly rearranging its own drainage. And this is the point at which the physical system stops being an abstraction, because there is one edge of the North Slope where the thawing is not subtle, where the rate is measured not in inches of settlement, but in yards of ground per year, and where you can watch the entire mechanism operate in a single summer. That edge is the coast. There's a place on the Beaufort Sea coast, between Utqiagvik and the Colville River Delta, called Drew Point. On a map, it's barely a feature. The shoreline there is a low line of bluffs, most of them between about 5 and 23 feet high, averaging around 14.5 feet above the water. Behind them, flat tundra with polygon patterning running inland as far as anyone cares to look. Drew Point is one of the fastest retreating shorelines in the United States, and it has been studied hard enough that we can watch the acceleration happen decade by decade. From 1955 to 1979, that coast retreated at an average of about 23 feet a year. That's already fast. Losing 23 feet of land per year, every year, is enough to reshape a map inside a lifetime. From 1979 to 2002, it went to about 31 feet a year. From 2002 to 2007, about 53. From 2007 to 2016, about 56 feet a year, averaged along a stretch roughly 5.5 miles long. 2.5 times the historic rate. And that is an average, which means some years and some sections did considerably worse. Zoom out to the whole Alaskan Beaufort coast, over 370 miles of it, from Utqiagvik east to the Canadian border, river deltas excluded. And the long-run average from the late 1940s through 2012 is something closer to 6 feet a year, which sounds mild until you notice the spread inside that average. Some sections gained land. Some lost more than 70 feet in a single year. The coast is doing a dozen different things at once. And where it does the extreme version, the reason is specific and knowable. So what makes Drew Point different? 3 things, and they stack. The first is what the bluffs are made of. We already said it, 80 to 90% ice by volume. A bluff like that is not a cliff of dirt being scoured by waves. It's a cliff of ice with sediment suspended in it. And it fails the way ice fails, not the way rock fails. The second is the orientation and exposure. Drew Point faces roughly northeast into the direction that summer storms come from, with no barrier islands offshore to take the energy out of the waves. Along the sections of this coast that do have barrier islands in front of them, erosion rates run at roughly a third of what the exposed sections see. That's a big protective effect, and it's a good reminder that geometry matters as much as temperature. The third is the water itself, and this is the one that has changed most in the last 40 years. For most of the 20th century, the Beaufort Sea in front of this coast was ice-covered for the great majority of the year. Sea ice does 2 things for a shoreline. It armors it. You cannot generate meaningful waves against a bluff if there's a lid of ice welded to the beach. And it limits the fetch, the open distance over which wind can build a wave, even after the ice pulls away from shore. Take the ice away for longer each summer, and you get both more time for wave attack and bigger waves during that time. You also get warmer water because open, dark ocean absorbs sunlight that white ice reflects. The near-shore open water season at Drew Point roughly doubled between 1979 and 2009, going from something like 45 days a year to something like 90. Across the years 2007 through 2016, it averaged about 91 days, ranging from about 71 days in the shortest year to 107 in the longest. 3 months of open water in front of a cliff made mostly of ice. Now here's the mechanism, and it is worth getting exactly right because the intuitive picture is wrong. You'd assume erosion here works like erosion anywhere. Waves hit the bank, knock material loose, carry it away, repeat. Sandpaper. Slow attrition from the front. That is not what happens. What happens is thermoabrasion, and it's closer to undermining than to grinding. Warm seawater. And in late summer, the water along this coast can run several degrees above freezing, which is scaldingly warm relative to ground that has sat at 16 degrees Fahrenheit for millennia. Washes against the base of the bluff. It doesn't have to be violent. It just has to be liquid and above freezing and in contact. The ice in the bluff face at the waterline melts. The sediment that was held in that ice falls out and gets carried off by the water. Now there's a small notch at the base of the cliff. Water gets further in. It melts more ice. The notch deepens. That's called a thermo-erosional niche, and it can run back into the bluff many feet, while the surface of the tundra above it stays completely undisturbed. From the top, the ground looks normal. There's grass. There are polygons. There's nothing to see. Underneath, the cliff is being hollowed out. Eventually, the overhang exceeds what the frozen material can support in tension, and the whole block fails. A slab of tundra, sometimes yards across, breaking along the pre-existing weakness in the ground, which on this coast is usually an ice wedge because that's where the material is weakest and the geometry is already vertical. The block tips into the sea, floats for a while because it's mostly ice, and disintegrates. That's why the coast has a serrated, blocky look where it's failing, and why the failures happen in bursts. This shoreline doesn't retreat smoothly. It stands still and then loses a room-sized piece of itself in an afternoon, and it does most of its year's work in a very short window. Erosion here is not spread evenly across those 90 days of open water. It concentrates in storm events, when wind pushes water levels up against the bluff toe and puts warm water in contact with ice that had been sitting above the normal water line all summer. One serious storm can do what a month of calm water cannot. There's a second process working the same face from above: thermodenudation, thaw slumping, where the exposed top of the bluff, now sitting in sunlight with its insulating vegetation gone, melts back and slides down. The two processes are not independent. Undercutting from below exposes fresh ice faces to the sun. Slumping from above dumps material at the toe that briefly protects it. The two are coupled, which is part of why predicting an individual year's retreat is hard even when the decadal trend is obvious. Now, what's in the material going into the water? This is where the coastal story and the carbon story fuse, and where I have to be careful, because this is the part of Arctic science that gets overstated most often. Researchers who sampled the bluffs at Drew Point found a clear vertical structure. The upper section, the Holocene age soils and old lake deposits, roughly the top 10 feet, is organic rich, averaging around 12% total organic carbon by mass. The lower section, the Pleistocene marine sediments, is much leaner, around 1%. So the old carbon in that bluff sits mostly in a rich cap over a much leaner base, and the erosion is taking both. Multiply the retreat rate by the bluff height by the carbon content along that 5.5-mile section, and for the period from 2008 to 2018, you get an export of roughly 12,000 tons of organic carbon per year into the Beaufort Sea from that one short stretch of coastline. The researchers noted that this is on the order of what a substantial river delivers annually. Coming off a length of coast, you could walk in a couple of hours. That's a real measured number. What happens to that carbon after it enters the water is much less settled. Some of it is respired by microbes and comes out as carbon dioxide. Some of it is buried in nearshore sediments and effectively restored. The partition between those fates is an active research question, and anyone who tells you confidently that all of it becomes atmospheric carbon is going beyond what the evidence supports. I want to flag that distinction now because we're about to look at a much larger number, and the honesty of the number depends entirely on keeping that distinction intact. But before we leave the coast, there's a consequence of this mechanism that has nothing to do with carbon and everything to do with what people built here. A coastline that retreats by undermining does not give warning. A beach that erodes gradually announces itself. The setback is visible while it happens, and it can be planned around. A bluff that hollows out invisibly and then drops 50 feet of ground in one storm does not. The land looks fine right up until it isn't there, which means that anything sited near this coast on the assumption that the shoreline was more or less where the map said it was, a house, a runway, a fuel tank, a cemetery, a wellhead, has a different risk profile than its builders understood. And people did build near this coast, extensively, for reasons that made complete sense at the time. A word about how anybody knows those retreat numbers, because the method is half the story, And it's the part that convinces me. 1955 is the first date in that Drew Point series for a specific reason. That's when there's usable aerial photography of the coast. Military and survey aircraft flew the Alaskan Arctic in the post-war years and shot photographic runs of the shoreline. And those frames are the baseline. Somebody in the 21st century sat down, geo-referenced 70-year-old photographs, traced the bluff edge on them, and compared that line against a modern one. Then the record improves in steps, and each step lets you see something the previous one couldn't. Later, aerial surveys give you the 1970s and the turn of the century. Commercial satellite imagery at high resolution gives you individual years, which is how the 2007 to 2016 figure exists at all, as an annual series, rather than a difference between two distant snapshots. And more recently, constellations of small satellites that image the same ground repeatedly give researchers something better still. Retreat measured within a single summer, week by week. That last capability changed the picture in a way I didn't expect. When you can only compare year to year, erosion looks like a rate. 56 feet a year sounds like a process that runs steadily, the way a clock runs. When you can watch inside the season, you see that it doesn't. The coast sits there doing very little for long stretches, then loses a startling amount in a few days when the conditions line up. A storm with the right wind direction pushing water up against bluffs that have been warming in the sun. The sea reaching ground it hasn't touched all summer, and blocks going in one after another. The annual number is real. It's just an average over a process that is almost entirely episodic, which has a practical consequence that anyone planning around this coast has to live with. If your site is 800 feet from the bluff edge, and the average retreat is 30 feet a year, the tempting conclusion is that you have 26 years. But averages are built out of quiet years and violent ones, and a single severe storm on this coast can take 50 to 100 feet. Stack 2 bad seasons, and the schedule you built your budget around is wrong by a decade. That's why the Federal Inventory of Abandoned Government Well Sites on the North Slope uses a 5-year window in its highest risk category, rather than a calculated arrival date. They're not predicting when the ocean gets there. They're flagging which sites are close enough that the question is now live. And it's why the variation along this coast matters as much as the headline. Over 370 miles of Alaskan Beaufort shoreline, the long-run average retreat is around 6 feet a year, and inside that average, some sections are gaining land, while others lose more than 70 feet in a year. The difference between a sheltered section behind a barrier island and an exposed ice-rich bluff facing northeast into the storm track is a factor of 3 or more, and it's set by things a map already shows. What the ground is made of, how tall the bluff is, which way it faces, and whether there's anything offshore to break the waves. None of which is mysterious, all of which was knowable, in principle, before anyone built anything. Most of it simply wasn't the question anybody was asking in 1949, when the priority was getting a rig onto a site before the ice went out. Before the built layer, though, the inventory, because the ice cellar question, what is this ground and what happens as it changes, has a second half that nobody dug a hole to find out. The frozen ground of the Northern Hemisphere holds an enormous quantity of organic carbon, and the reason is a kind of accounting error in the way cold places handle death. In a temperate forest, a leaf falls, and within a season or two it's gone, eaten by fungi and bacteria, broken down into carbon dioxide and simpler compounds. Most of the carbon returned to the air. The soil holds some, but it's a working balance. Carbon comes in through photosynthesis and goes out through decomposition, and over long periods the two roughly match. In the Arctic, the second half of that transaction runs slow. Plants still grow. The tundra is surprisingly productive in its brief season, and there are years the whole coastal plain flushes green. But when that material dies, the decomposers that would normally consume it are working in cold, waterlogged, oxygen-poor conditions for most of the year and frozen solid for the rest. Decomposition doesn't stop. It just falls behind. Do that for 10,000 years, and you accumulate peat. Do it while the ground surface is slowly rising, as sediment blows in and settles, and new plant material grows on top, and the older material at the bottom gets buried below the depth that thaws each summer, pushed down into the permanently frozen zone, where the biological clock stops almost entirely. That's the mechanism. Organic matter that was on its way to being recycled got interrupted partway through and filed underground. The current best estimate is that the northern permafrost region holds somewhere in the range of 1,460 to 1,600 billion metric tons of organic carbon. Roughly 2/3 of it sits in the upper 10 feet of ground. That region is about 15% of the Earth's soil area, and it holds a wildly disproportionate share of the Earth's soil carbon. For a comparison that means something, that's on the order of twice the amount of carbon currently in the entire atmosphere. Now, that number gets used badly all the time, so let me lay out what it does and does not mean, and then we'll go back to the specific ground under the North Slope. It does not mean that a lot of carbon is poised to enter the atmosphere. It means it exists in the ground, in a form that is currently not participating in the atmosphere. Whether any given ton of it ever does depends on a stack of conditions, whether that particular ton thaws at all, whether it thaws wet or dry, whether there's oxygen present, and what the microbial community there can actually metabolize. How much gets taken up again by plants growing in the warmer, longer seasons on top, and how much simply gets buried a second time in a lakebed or a nearshore sediment before anything can eat it. Those variables push in different directions, and some of them push hard. Warmer Arctic summers grow more vegetation, and more vegetation pulls carbon down. Tundra greening is one of the best documented Arctic trends there is. Some parts of the permafrost region are net absorbers of carbon in the growing season and net emitters over the full year. Some sites flip between the two, depending on the year. So the honest statement is this: the permafrost region as a whole appears to have shifted from being a net carbon sink to being a net carbon source, with recent estimates of the release running somewhere around 3 to 6/10 of a billion tons of carbon per year across the entire circumpolar region. Those estimates come with genuinely wide error bars. They are extrapolated from a monitoring network that is thin relative to the size of the region, and the field's own reviews say so. That's the difference between poorly sampled and unresolved, and it's worth keeping straight. How much carbon is in the ground is reasonably well constrained. That's a question of drilling cores and measuring. And a lot of cores have been drilled, though coverage is much better in some regions than others. How fast it comes out, and what fraction ends up airborne rather than reburied or regrown, is where the genuine scientific uncertainty lives. One of those is a sampling problem. The other is a mechanism problem. Treating them as the same kind of unknown is how you end up either terrified or dismissive, and neither is warranted. What is not uncertain is the physical character of some of what's down there, and here the North Slope has a particular specialty. There's a class of permafrost called Yadoma. It's a Siberian word, and the Siberian deposits are the famous ones. But Yadoma-type ground occurs across Alaska and the Yukon too, and it is the extreme case in every direction that matters. Yadoma is late Pleistocene material, Ice Age ground, built up during the last glaciation when much of this region was cold, dry, unglaciated steppe. Windblown silt accumulated, ice wedges grew through it, the surface kept rising, and the whole package froze in place and stayed frozen for tens of thousands of years. What you end up with is a deposit that can run tens of feet thick, that is 50 to 90% ice by volume, and that carries roughly 2% carbon by mass throughout. 2% doesn't sound like much until you multiply it by the volume. The Yadoma region, spanning more than 1 million square kilometers from northeast Siberia across to Alaska and Canada, is estimated to hold somewhere between 210 and 500 billion tons of carbon on its own. And Yodoma has a property that ordinary permafrost doesn't. Because the ice content is so high and the ice is concentrated in massive wedges rather than distributed as pore ice, when Yodoma thaws, it doesn't settle a little. It collapses spectacularly. That's the ground that produces the biggest thaw slumps, the deepest thermokarst lakes, the features that look like a bite taken out of a hillside. And because the collapse exposes a tall face of previously buried material all at once, it can bring deep old carbon into contact with air and water on a timescale of a single season. Instead of the century-scale timescale you'd get from the thaw front creeping down an inch or two at a time. That's the distinction between gradual thaw and abrupt thaw, and it matters because gradual thaw is what most of the older climate models represented, and abrupt thaw is what a lot of the actual landscape does. Now put that back on the North Slope specifically, and add the honest caveat this region deserves. The Arctic coastal plain of northern Alaska is not the heart of Yodoma country. The classic thick Yodoma is more characteristic of interior and western Alaska, and above all, of Siberia. What the North Slope coastal plain has is its own version of the same problem. Ground that is extraordinarily ice-rich near the surface, with an organic-rich Holocene cap over leaner Pleistocene material below, and a landscape architecture, the ice wedge polygon net, that is built to collapse into troughs and ponds when the top of the wedges goes. Which means the North Slope's carbon story has less to do with a colossal buried reservoir suddenly venting, and more to do with a slower, messier, harder-to-model set of processes. Active layers deepening a fraction of an inch at a time, wedge tops melting, troughs deepening, drainage rearranging, lakes forming and draining, and a coastline, delivering measured tons of ancient organic material into the sea every single year. The coastal number is the one I trust most because it's the most directly measured. You can photograph the bluff, measure the retreat, core the material, run the carbon content, and multiply. 12,000 tons a year off 5.5 miles of coast. Extend that logic along the full length of an Arctic coastline that's mostly ice-rich permafrost, and the fluxes get large, and they are large right now, not in a projection. There is one more piece of this that deserves saying, because it changes what the word release means. Carbon that comes out of thawing permafrost doesn't come out as one gas. In dry, oxygenated conditions, a thawed hillside that drains, microbes respire it aerobically, and you get carbon dioxide. In waterlogged conditions with no oxygen, the bottom of a thermokarst pond, a flooded trough between polygons. A different microbial community does the work and produces methane. Methane is a far more powerful greenhouse gas per molecule over the short term, though it also breaks down in the atmosphere within a couple of decades, while carbon dioxide effectively persists. So the same thawing ground can produce very different climate consequences depending on something as mundane as whether the water drains. And whether the water drains depends on the local topography, which is being rearranged by the thaw itself, which is why this is so hard to predict and why the responsible scientific literature reads as hedged as it does. I'll give you my own read. For what it's worth, the frustrating thing about the permafrost carbon question is not that we don't know it matters. It clearly matters. The frustrating thing is that its magnitude sits inside a range wide enough to support almost any rhetorical position you'd like to take. And the range is wide for boring reasons. Not enough measurement sites over not enough years, in a region the size of a continent that costs a fortune to work in. Which brings me back around to where we started. Because the ice cellars are a small, unglamorous, extremely local version of the exact same problem. And they came with one huge methodological advantage. Somebody had already dug the holes. Every one of those 71 cellars in Utqiagvik is a shaft into the top of a permafrost column, in a place with 150 years of settlement history, with people going up and down it several times a year and noticing things. That's a monitoring network that nobody had to build, run continuously for generations, with observers who had a direct and serious stake in whether the readings were accurate. And they are the reason the question stops being academic, because the ice and the ancient carbon are only the first thing buried in this ground. The second thing is younger by about 50,000 years. We know exactly who put it there, and it was installed on the same unexamined assumption as the cellar, that whatever else changed up here, the ground would hold. That assumption became a foundation. Then it became a road. Then it became one of the largest industrial complexes ever built at that latitude by anybody. On the 12th of March, 1968, a well called Prudhoe Bay State No. 1 found oil on the Arctic coast of Alaska. What it found turned out to be the largest oil field in North America, something in the neighborhood of 25 billion barrels originally in place, under a footprint of roughly 330 square miles of coastal tundra. Everything on the modern North Slope descends from that well. But finding the oil and moving the oil are two different engineering problems. And the second one was, in some ways, harder, because between Prudhoe Bay and the nearest road was about 400 miles of ground that had never carried a vehicle heavier than a dog team. And nobody in the American construction industry had much experience with what that ground would do if you drove on it. They found out fast. And the way they found out is one of the best lessons this landscape has ever taught. In November of 1968, the state of Alaska began building a winter road north from Livengood, north of Fairbanks toward the new oil field. The idea was straightforward and on its face elegant. Winter road, frozen ground. Push the snow off, run trucks over the frozen surface, haul equipment up to the slope, and when spring comes, the road melts, and nature takes it back. Cheap, fast, temporary. They called it the Walter J. Hickel Highway, after the governor. 400 miles of it, finished by March of 1969. What the bulldozers did in pushing the snow aside was strip the insulating vegetation off a long, thin band of ice-rich ground. By April, it was over. That summer, the exposed ground thawed. The ice in it melted, the surface slumped, and the corridor filled with water. What had been a road became a linear pond running 400 miles across interior and northern Alaska, and it acquired a nickname that has outlasted almost everything else about it: the Hickel Canal. I'd love to be able to tell you that this was some inexplicable oversight. It wasn't exactly. Permafrost engineering existed as a discipline. The Army's cold regions researchers had been publishing on it for years, and plenty of people in Alaska could have told you what would happen. It's more that the project moved at the speed of a boom, and the assumption that frozen ground is just ground survived contact with reality for exactly one summer. The rebuild was different. When the Haul Road to Prudhoe was constructed properly in 1974, the James W. Dalton Highway, 414 miles, 390 of them, laid down in a single 5-month push. The fundamental design decision was the opposite of what the Hickel Road had done. Instead of removing material to make a surface, they added it. Thick gravel, on the order of 3 to 6 feet deep, laid directly on top of the intact tundra mat. The gravel does more than provide a driving surface. Its main job is insulation. It's a thermal blanket engineered to keep the summer heat from reaching the ice below, so the ground under the road stays frozen and keeps behaving like a foundation. Same reason the drilling pads and the airstrips and the building sites at Prudhoe Bay all sit on thick gravel pads. The entire built environment of the North Slope is designed around one rule, and that rule is, do not let the ground under it thaw, which is a strange thing to notice about a landscape. The oil field is not built on the tundra. It's built on a layer of imported rock whose job is to keep the tundra frozen. The infrastructure and the permafrost are in a relationship, and the infrastructure is the one doing the maintaining. Today, the Dalton runs from the Elliott Highway up over Atagun Pass in the Brooks Range at about 4,700 feet and down onto the coastal plain to Dead Horse. Only about a third of it is paved. There are 3 places to buy fuel along the entire length. It carries something like 160 trucks a day in summer and 250 a day in winter, and it is, in a real sense, the supply line for the whole northern edge of the state. And it's had problems of exactly the kind you'd predict. The most publicized was not permafrost directly, but a river. In the spring of 2015, the Sagavanirktok River, which the highway runs alongside for its final stretch, overtopped and flooded the road near Dead Horse badly enough to close it for days and require an emergency response and a very expensive repair. That kind of event has recurred. Rivers on the coastal plain are constrained by frozen ground and by the massive ice that builds up in their beds through winter. And when the melt comes fast, the water goes wherever it can, which is sometimes over the only road. The subtler and more chronic problem is the road settling into ground that isn't holding it as well as it used to. Thaw settlement under a road doesn't look like collapse. It looks like a dip. It looks like a section of pavement that needs more gravel this year than it needed last year. It shows up as a maintenance budget going up and as a highway that requires continuous feeding to stay flat. Now, next to the road for its entire length runs the object that made all of this necessary. The Trans-Alaska Pipeline is 800 miles long, and for about 420 of those miles, it runs above the ground entirely, 5 or 6 feet up off the tundra, running on H-shaped steel frames called vertical support members. There are around 78,000 of those supports. That design decision was not aesthetic. Hot oil comes out of the Prudhoe Bay Reservoir at well over 100 degrees Fahrenheit, and it stays hot as it moves. Bury a pipe carrying that fluid in ice-rich permafrost, and you have installed a 400-mile heating element into a foundation that only functions while frozen. The pipe would thaw a corridor around itself, the ground would settle unevenly beneath it, and a steel pipe under strain in unevenly settling soil is a pipe that eventually fails. So wherever the ground was ice-rich, they lifted the pipeline off it entirely and let the air circulate underneath. Then they went further, and this is the piece of engineering I find most elegant. Each of those support members had to be anchored in the permafrost itself, and driving a steel pile into frozen ground creates a small amount of heat and disturbance around it. To make sure the ground around the anchors stayed frozen, permanently, without anybody having to run a machine, the designers fitted a great many of the supports with thermosiphons. A thermosiphon is a sealed tube with a working fluid inside it, usually ammonia. The bottom end is buried in the permafrost. The top end sticks up into the air, finned like a radiator. When the air outside is colder than the ground, the fluid at the bottom of the tube absorbs heat from the soil and evaporates. The vapor rises. It condenses against the cold upper section and gives up that heat to the atmosphere, and the liquid runs back down the wall of the tube to do it again. It has no pump, no power supply, no moving parts, and no way to run backward. When the air is warmer than the ground in summer, the cycle simply stops. It is a one-way heat valve, driven entirely by the Arctic winter that pumps warmth out of the ground and throws it away into the sky. There are somewhere around 120,000 of them arrayed along the pipeline route, sunk anywhere from about 15 feet to about 70 feet into the ground. On a clear day along the Dalton, the silvery poles standing beside the pipeline supports are those. Most people who drive that road have no idea they're looking at a refrigeration system holding up a pipeline. The same technology is under a great deal of the Prudhoe Bay complex. Buildings up there don't sit on slabs on grade. They sit on pilings driven into permafrost, usually with an open airspace underneath so the winter cold can get at the ground and carry the building's own heat away rather than letting it soak downward. Where that wasn't enough, they converted the pilings to thermopoles. Same principle, the pile itself becomes the heat pump. That conversion actually happened, and the reason it happened is instructive. In the early 1980s, a large facility at Prudhoe Bay containing gas turbine compressors started to settle. The measured movement was on the order of 0.8 of an inch in a year. Under a house, 0.8 of an inch is a crack in the drywall. Under a rotating machine that has to stay aligned to a fraction of that, it's a serious problem. About 400 of that facility's piles were converted to thermopoles to arrest it, 0.8 of an inch. That is the scale at which this failure mode operates. No sinkhole, no dramatic collapse, a machine going slowly out of true because the ground beneath one corner of the building is a little warmer than the ground beneath another. So the engineering answers exist. That's an important thing to say plainly, because the version of this story that treats Arctic infrastructure as doomed is wrong and also insulting to the people who spent 50 years figuring out how to build up there. Gravel pads, elevated structures, air gaps, insulation layers, thermosiphons, thermopoles, adjustable foundations that let you re-level a building, engineered thaw-resistant fills. All real, all in use, all working. The catch is that every one of those solutions was sized against an expectation about how much the ground would warm. And the expectation was set decades ago. The size of that gap showed up on a stretch of hillside at milepost 734. In 2020, operators of the Trans-Alaska Pipeline applied to the state of Alaska for permission to do something that, as far as anyone involved could determine from the records, had not been done before. An 810-foot section of the line runs across a slope of ice-rich permafrost north of Fairbanks. That slope had begun to move. Slowly. This is creep, not a landslide, but enough that several of the vertical supports holding the pipeline had visibly twisted and bent. The state's own analysis of the proposal put it about as directly as a permitting document ever does. The project was integral to the protection of the pipeline. The fix was more of the same medicine, applied for a new reason. About 100 freestanding thermosiphons, driven 40 to 60 feet into the ground, plus a 3-foot layer of wood chips laid over the surface as insulation, with roughly 120 days of construction to install it all. Refrigerate the hillside. Stop it moving. What makes that episode worth pausing on is not that the pipeline was in imminent danger. It wasn't. The problem was caught, and the fix is well understood. And thermosiphons are proven technology. What's notable is the category. The thermosiphons along the original pipeline route were installed as a preventive measure, part of the design, to keep frozen ground frozen. The ones at milepost 734 were installed as a remedy, after a slope had already started to fail, to try to refreeze ground that had begun letting go. Officials looking through the pipeline's history could not find a prior instance of either thing, of slumping permafrost damaging the supports, or of thermosiphons being deployed defensively after a slope was already sliding. Same tool, different verb. That's what a changing baseline looks like from the inside, a maintenance department discovering that its preventive equipment has quietly acquired a second job. And there's a version of this that touches far more people than the pipeline does, because it governs when anybody is allowed to move anything on the north slope at all. Almost all of the oil and gas activity on the slope that isn't sitting on a permanent gravel pad happens in winter. On ice, the reasoning is entirely about protecting the tundra. Drive a heavy vehicle across the coastal plain in summer and you crush the vegetation, break the insulating mat, and start exactly the process that ruined the Hickle Road. Do it once and you leave ruts. Do it repeatedly and the ruts collect water. The water absorbs heat. The ground beneath thaws deeper, and the rut becomes a permanent channel that reorganizes the drainage around it. Tracks made by vehicles on the Alaskan tundra decades ago are still visible today, and in places they're not tracks anymore. they're ponds. So the state built its rules around a simple physical principle. Wait until the ground is frozen hard enough and covered deeply enough with snow that the load spreads and the vegetation is protected, then let the traffic move. The current standards are specific. In the two coastal areas of the North Slope, the tundra opens to winter off-road travel when the soil temperature at a depth of 12 inches has reached 23 degrees Fahrenheit, and there's an average of 6 inches of snow on the ground. In the foothills area up against the Brooks Range, the requirement is the same soil temperature, but 9 inches of snow. State land managers run monitoring stations in each area through the fall and watch the numbers come down. When those conditions are met, the tundra opens, and once it's open, there's effectively no restriction on what kind of vehicle can run on it under permit. Everything moves at once. Drilling rigs, camps, fuel, pipe, the whole apparatus of exploration and construction. Ice roads get built, and building an ice road is its own remarkable process. Pumping water from tundra lakes, spreading it across a surveyed route in thin layers, letting each layer freeze, and repeating until the sheet is thick enough to carry a rig. Come spring, the whole thing melts and leaves nothing behind. It's the Hickel Highway idea done correctly. A road made out of added ice instead of scraped-away insulation. Then the tundra closes. When state assessors judge that thaw has made the snow too soft or too thin to travel without damaging the ground, they call it notify permit holders and give everyone 72 hours to get every vehicle and every piece of equipment off the tundra and onto the road system. After that, nothing moves off-road until the 15th of July at the earliest. And the reason for that later date isn't only the saturated soil, it's also that migratory birds are nesting out there, in numbers that would surprise you, on ground that looks empty and isn't. So the operating year on the North Slope is bounded by two dates that nobody chooses. The ground chooses them, and the window between them has been getting shorter. The original standards were set in the 1970s, and under those rules, the winter travel season ran on the order of 200 days a year. By the early 2000s, the season had been cut roughly in half, down around 100 days. That's the figure that's been cited in the technical literature on this, and it prompted a serious research effort into whether the old snow and frost thresholds were the right ones in the first place, which is part of how the current standards came to be written the way they are. Look at the recent record, and the variability jumps out. The date the tundra opens has ranged from as early as the 2nd of November to as late as the 27th of January. That is a spread of nearly 3 months in when the season starts. And in recent years, the foothills area, the one that needs 9 inches of snow, has not consistently opened at all. In years when the criteria aren't met, managers may open the tundra conditionally, with restrictions, allowing only the specially tested low-impact vehicles that are normally reserved for summer. Think about what that does to a project. If you are building anything on the North Slope that isn't on the road system, your entire construction season is that window. Your equipment has to get in and get out inside it. Your budget assumes a certain number of working days. And that number is not something you can nail down in advance because it depends on how much snow fell in October and how fast the ground gave up its summer heat. A season that opens on the 2nd of November and one that opens on the 27th of January are not the same project. They are barely the same industry. None of this is a story about an industry being punished. It's a story about a design assumption. Every road, pad, pipeline, building, airstrip, and ice road on the North Slope was engineered against a set of expectations about ground temperature, thaw depth, snow, and season length, and those expectations were established when the record looked stable. They aren't wrong so much as they are aging, and the cost of an aging assumption is paid in maintenance, in re-engineering, and in schedule. Somebody has tried to total that up for the state as a whole. A study published in the Proceedings of the National Academy of Sciences estimated the cumulative cost of climate-driven damage to Alaska's public infrastructure, roads, buildings, airports, pipelines, railroads, from 2015 through the end of this century. Without adaptation, under a high-emission scenario, the figure came out around $5.5 billion in constant dollars. Around 38% of the projected damage traced to near-surface permafrost thaw, with flooding of roads accounting for the largest single share overall. The more interesting number in that study is the second one. When the researchers modeled proactive adaptation, fixing things before they break, designing for the ground you're going to have rather than the ground you had, the projected cost dropped to roughly $2.9 billion, a saving on the order of $2.5 billion, achieved by treating the ground as a variable rather than a constant. That's a projection, with all the assumptions a projection carries, and reasonable people argue about the discount rates and the damage functions. But the direction is not really controversial, and it lines up with what the engineers on the ground have been doing for years anyway. The Prudhoe Bay facility that converted 400 piles to thermopiles in the 1980s did that math a long time ago, without needing a paper to tell them. So the human layer on the north slope turns out to be a layer of thermal management, gravel to insulate, air gaps to ventilate, thermosiphons to actively pull heat out, season rules to keep loads off the ground until it's hard. A whole industrial province operating on the principle that its foundation is a material that must be kept below a threshold, and that everything above it is a life support system for the ground, which is exactly the same principle as an ice cellar, at a scale about 1 million times larger and with a budget. There's one resource that whole system runs on that I skipped past, and it turns the ice road story back into a permafrost story. To build an ice road, you need water. A lot of it. You are, after all, manufacturing a road-sized slab of ice out of liquid, one thin layer at a time, and the volumes involved are enormous. On the Arctic coastal plain, there is exactly one place to get water in midwinter, and that is the lakes. Which raises an obvious question. Why is a place with almost no precipitation covered in lakes? Because of the permafrost, and specifically because of thermokarst. The coastal plain of northern Alaska is one of the most lake-dense landscapes on Earth. From any altitude, it reads as more water than land in places, thousands upon thousands of shallow ponds and lakes, many of them oddly oriented in the same direction, elongated roughly northwest to southeast in a pattern regular enough that it looks deliberate. The orientation has been debated for the better part of a century, and probably comes down to prevailing wind-driving circulation that erodes particular shorelines faster than others. But the lakes exist in the first place, because ground with that much ice in it, when it thaws locally, subsides. A depression forms. Water collects in it. Water is dark and it stores summer heat, so the ground under the pond thaws deeper than the ground around it, so the depression deepens, so the pond grows. That's a thermokarst lake, a hole in the ground made by its own melting, and they don't last forever. As a lake expands, it can eventually cut through to a drainage, a stream channel, an ice wedge trough, a neighboring lower basin. And when it does, it can empty, sometimes over a matter of days. What's left is a drained lake basin, a flat, wet, unusually productive patch of ground that immediately starts refreezing from the top, growing new ice wedges, and beginning the cycle again over centuries. Enormous parts of the North Slope are drained lake basins in various stages of that cycle. The landscape works as a slow rotation between lake and land, driven entirely by the freezing and thawing of ice in the ground. So when a company pumps water out of a tundra lake in January to build an ice road that will let it move a drilling rig, it is drawing on a landscape feature that exists because permafrost thaws. There's something almost circular about it that I don't think gets appreciated. There are rules about that withdrawal, and they're built on ice. A shallow Arctic Arctic lake freezes from the top down through the winter, and a lake that freezes solid to the bed kills the fish in it and loses the overwintering habitat that a lot of the coastal plains ecology depends on. So the amount of water that can be taken is limited by how much liquid remains underneath the ice, which means the volume available to build roads in a given winter is set by how thick the lake ice got, which is set by how cold the winter was and how much insulating snow fell on top of it. Follow that chain all the way through and you get something unexpectedly tidy. How much industrial activity can physically happen on the North Slope in a given year depends on the temperature of the ground, the depth of the snow, and the thickness of lake ice. Not on the price of oil, not on permitting, on 3 physical measurements taken in the field, in the dark, in November. The thing all that machinery exists to serve is still 6 decades on, the field at Prudhoe Bay. And its arc says something too. Production started on the 20th of June, 1977, when the pipeline was finished. It climbed to a peak of about 1.5 million barrels a day in 1988. By 2023, it was running somewhere in the vicinity of 320,000 barrels a day. Over its life, the field has produced more than 13 billion barrels. It still has roughly 1,100 producing wells, and by recoverable reserves, it still ranks ahead of every other field on the continent. A field in that stage of life is a maintenance operation more than a discovery operation. And maintenance on the North Slope means exactly what it's meant this whole time, keeping the ground under everything cold enough to hold the equipment up. Every year, the pads, the roads, the piles, the thermosiphons, and the flow lines get inspected and adjusted against a foundation whose temperature is drifting in a known direction. And it works when somebody is watching. There's a category of thing on the North Slope where nobody was watching, where the equipment went in, the job finished, the crews withdrew, and the assumption that the ground would hold whatever was left in it indefinitely, without further attention, was never revisited by the people who made it. There are more than 100 of them out there. Some have been out there for more than 80 years. In 1923, a large section of northern Alaska was set aside by the federal government as an oil reserve for the United States Navy, Naval Petroleum Reserve No. 4. The Navy had converted from coal to oil. Oil was strategic, and there was a persuasive geological argument that there was oil up there, an argument that rested in part on the fact that people living on that coast had known about seeps of oil-bearing material for a very long time and had used it. For 2 decades, nothing much happened. Then came the Second World War, and suddenly, a domestic strategic petroleum reserve at the top of the continent stopped being a filing cabinet asset. Between 1944 and 1953, the Navy ran a drilling program on that reserve. Later, from the mid-1970s into 1982, the United States Geological Survey ran another. Between them, the 2 programs drilled 136 exploratory and scientific wells across an area now called the National Petroleum Reserve in Alaska, a chunk of the western North Slope roughly the size of Indiana. Understand what that meant logistically in the 1940s. There were no roads. There was no Dalton Highway. There wouldn't be for 30 years. Everything. Rigs, casing, fuel, diesel, food, housing, the drilling mud, the men, came in by ship through a few weeks of open water, or by aircraft onto gravel strips in frozen lakes, or overland in winter. Camps were built and run through polar night. Wells were drilled through hundreds of feet of permafrost before they reached anything a geologist wanted to look at. It was an extraordinary operation, and it operated under the standards of its time, which is a phrase doing a lot of work. When a well was finished, the crews did what crews did then. Some wells got cement plugs to isolate the formations they'd penetrated. Some got partial plugs, some got none. Equipment that was expensive to fly out was left where it stood: casing, pipe, drums, batteries, refrigerant lines, whole buildings, reserve pits. The excavations that hold drilling mud and cuttings were left in the ground. In several cases, Diesel fuel was deliberately poured down the wellbore because diesel doesn't freeze at Arctic ground temperatures and a fluid-filled hole stays open, which meant scientists could keep lowering thermometers down it for years afterward. That last detail is worth holding because it is the hinge of this entire chapter. A number of these wells were not abandoned in the ordinary sense. They were repurposed as instruments. Some of the very holes drilled looking for oil in the 1940s and 50s became and remain the long-term permafrost temperature record for northern Alaska. Those deep boreholes that the Geological Survey has been reading since the late 1940s. The ones whose bent temperature profiles revealed decades of surface warming that no weather station had documented. The wells that told us the ground was warming are, in part, the same wells that are now a problem, because the ground is warming. I don't think there's a neater illustration of what this whole story is about. Responsibility for the reserve moved to the Department of the Interior in 1976, and in 1982 the Bureau of Land Management inherited the job of assessing, plugging, and cleaning up all 136 of those wells. It has been working on that ever since, and it has spent close to $235 million on it. Here's where the inventory stands, and I find the categories more revealing than the totals. 97 of the wells require no further action from the agency. Some of those were plugged and remediated properly over the decades. A long list of names that reads like a gazetteer of places most people have never heard of. Umiat, Umalik, Inigok, Titaluk, Square Lake, Grandstand, Wolf Creek, Knifeblade, Fish Creek, Cape Halkett, Echo Bay, Tulageek. Others were shallow, uncased core holes with nothing in them worth worrying about. 19 were handed out of federal ownership altogether, to the North Slope Borough. 16 wells are still in active use by the Geological Survey for permafrost temperature monitoring. They're not abandoned. They're operating scientific instruments, and they'll need plugging and surface cleanup eventually, when the research no longer needs them. 6 wells currently require action, plugging and surface cleanup, and the agency estimates that finishing those 6 will cost somewhere between $60 and $100 million. 6 wells. Up to $100 million? That's the price of doing this kind of work in a place with no roads, a short working season, and a legal obligation to leave the ground clean. And 2 wells cannot be found. One is called Minga Velocity Test Number 1. It was a shallow hole drilled into a lake to measure how fast seismic waves travel through permafrost. A purely scientific hole, no oil or gas encountered, only the top 27 feet cased. Nobody has located it. The other is Sentinel Hill Core Test Number 1. It was drilled along the Colville River in 1947, and shortly after it was completed, a landslide came down and buried it. It has been under there ever since. Its precise location is unknown. The agency's assessment is that there's no evidence of surface or subsurface risk at the estimated position, and if it's ever located, they'll reevaluate. A well swallowed by a hillside in 1947 and never seen again. I'd call that a fair summary of how this landscape treats things left on it. Now to the part that connects directly back to Drew Point. Among the wells the agency is still responsible for, the ranking system it uses to decide what gets attention first has a specific criterion at the top of its highest risk category. A site earns a high surface risk rating if it may be adversely affected by coastal erosion within 5 years. Leaks and contamination are ranked separately. This criterion is about the shoreline arriving, and the plan states the agency's standing commitment to regularly inspect every site within 1,000 feet of the Beaufort Sea shoreline, specifically to track the rate of coastal erosion and the erosional stability of the site. 1,000 feet. Given retreat rates on parts of this coast, 1,000 feet is not a comfortable buffer, it's a countdown. The clearest case is a well called East Simpson Number 1. Its subsurface risk is rated low. There are plugs in place isolating the productive zones, and the hole is currently full of diesel and in use by the Geological Survey as a temperature monitoring well. That's the well-doing science. Its surface risk is rated high because the reserve pit associated with it, the excavation holding the old drilling waste, sits approximately 800 feet from the advancing shoreline. The coast there is coming in at roughly 25 to 50 feet a year, and, the agency notes, it is possible to lose between 50 and 100 feet of coastline in a single severe storm event. Do the arithmetic in your head and it's uncomfortable. 800 feet at 25 to 50 feet a year is somewhere between 16 and 32 years, assuming nothing accelerates and no storm takes an unusual bite. The reserve pit was characterized in the winter of 2023 specifically to determine what's in it and how much of it has to come out. East Simpson No. 1 has been reclassified. It used to be on the list of temperature monitoring wells, quietly doing its job. Coastal erosion moved it onto the list of wells requiring action. Another one, West Dees No. 1, has been added to the watch list for the same reason. Not because it's threatened yet, but because the erosion activity nearby has increased enough to warrant keeping an eye on it. And the agency has said openly that it doesn't plan to plug the monitoring wells while the survey still needs them, unless the coast forces the issue. That's the whole story in one administrative sentence. A research schedule set by scientists and an eviction date set by the sea, and the second one wins. There is precedent for how this goes. A well called J.W. Dalton No. 1 was drilled near the coast in the late 1970s. By the mid-2000s, the shoreline had closed on it, and it was cleaned up and plugged. According to reporting at the time, more than 300 feet of shoreline in that vicinity went in a single summer, and the site of the well is now underwater. It appears on the agency's list today in the column of wells that require no further action, which is true, and which is a slightly eerie thing to read, because the reason it requires no further action is that the work got done before the ocean arrived. The rest of the remaining list reads like an inventory of the era that produced it. At Tapagorok No. 1, there is the surface risk is high because of what's lying around on the ground: battery cores, extensive refrigerant piping, drilling muds. Refrigerant piping. Because of course the camp had a way of keeping things cold, and of course it was left there. At Skull Cliff Core Test No. 1, there are about 54 feet of diesel standing in the wellbore, roughly 16 barrels of it, put there decades ago precisely so the hole wouldn't freeze shut and temperature measurements could continue. The site sits in a travel corridor that people use between Utqiagvik and Wainwright, which is part of why it matters. Solid waste there was cleaned up in the summer of 2025. At Mead No. 1, the concern is a refrigeration system buried under the tundra and the possibility of diesel leaking from it into the surrounding soil. Read those three descriptions together and something odd surfaces. In each case, the thing creating the modern risk is a piece of cold management equipment. Fluid, put down a hole to stop it freezing. Refrigerant lines to keep a camp's stores cold. A refrigeration system buried in the ground. Everyone who has ever worked on the North Slope, in every era, has been in the business of managing temperature. The Inupiat cut a chamber in the permafrost and let the ground do it for free. The Navy flew in refrigeration machinery and poured diesel down boreholes. The oil industry installed 120,000 thermosiphons. Same problem, 3 different eras of answer, and the last 2 both left something in the ground that somebody now has to go retrieve. The wells are the archive of this landscape, and I mean that physically, a record of what a country believed about frozen ground at the moment it was building on it. In the 1940s, the belief was that the Arctic was a permanent freezer and that whatever you left in it would stay put. That belief was reasonable on the evidence available. It was also, in the specific sense that matters, a load-bearing assumption. Everything from a well plug to a reserve pit to a buried refrigerant line was designed against it. And the agency now inspecting those sites is doing something that would have made no sense at all to the people who drilled them, watching the coastline to figure out how long it has. It's worth looking at the shape of that drilling effort a little more closely because the names on the list tell you what people were actually doing out there. The Navy's own program ran the bulk of the work, drilling on the order of 90 test holes across the reserve in the years after the war. Another handful went down in the Barrow area through the 50s, 60s, and into the 70s. Then, in the late 70s and into the early 80s, a contractor working for the government drilled roughly 36 more. Different eras, different technology, same map. Read the inventory of what they drilled, and it stops sounding like an oil hunt and starts sounding like a survey of the unknown. There are the wells you'd expect: Umiat, Umalik, Inigok, Fish Creek, Square Lake, Keolak, Topogorok, Mead, Awuna, Lisburn, Tunalik. And then there are dozens of holes whose names announce that nobody was chasing a reservoir at all. Simpson Core, test number 1, through Simpson Core, test number 31. Almalik, foundation test number 1, through number 10. Foundation tests. Holes drilled to find out what the ground was, so somebody could work out what could be built on it. That is the entire story of the North Slope, compressed into an entry on an inventory. Before you can look for oil in a place like that, you have to establish whether the place will hold up a rig. The very first thing the United States did out there, at scale, was test the foundation. And a lot of what those holes found was permafrost, hundreds of feet of it, drilled through on the way down, logged and described because it was in the way. Some of that logging is now the earliest quantitative record anyone has of what the frozen column under the coastal plain looked like at the middle of the 20th century. The program did find hydrocarbons, though nothing on the scale of what turned up at Prudhoe Bay 2 decades later. There's a modest oil accumulation at Umiat, up the Colville, known since the 1940s and never commercially developed, because the economics of producing a small field several hundred roadless miles from anywhere never worked. There's natural gas near Utqiagvik, and 19 of the wells in that area, the South Barrow wells and 2 at Walakpa, were later handed out of federal ownership to the North Slope Borough under legislation written specifically for that gas field. So a handful of the holes became useful, 16 became scientific instruments, and most of the rest became something nobody had a word for at the time, which is a long-term obligation. The condition they were left in has produced some memorable cleanup work. Agency staff describing the job have talked about hauling trash, wood, gloves, and a pair of boots out of well bores that had thawed enough to give up their contents, material that got dropped down the hole at the end of a job, because flying it back out cost money and the hole was right there. That's not villainy. It's a crew at the end of a season in 1949 in the dark, with a plane waiting, making the same decision anybody would make about a hole in ground that everyone agreed was permanently frozen, which is the assumption again, in its smallest possible form. If the ground never changes, a hole is a place where things stop existing. The ground changed. So the hole is now a place where things are, and somebody has to go get them. So far, this has been a story about materials: ice, silt, gravel, steel, ammonia, diesel. It would be easy to leave it there, and a lot of coverage of the Arctic does because materials don't argue with your framing. But there are about 11,000 people living on the North Slope, in 8 communities spread across an area larger than most states, and they are not extras in a story about permafrost. They're the ones who noticed it first, they're the ones running the longest continuous observation record of that ground, and the decisions being made up there right now are theirs. Utqiagvik is the largest of those communities, roughly 5,000 people, a clear majority of them in Upiat, sitting at about 71 degrees north on a spit of coast between the Chukchi Sea and the Beaufort. There's no road to it. There never has been, and there isn't likely to be for the reasons this whole story has been about. You cannot casually run a highway across 400 miles of ice-rich ground. Everything arrives by air or by barge during the short window when the sea allows it. The sun goes down in mid-November and does not come back up until late January. The name is worth a moment because it says something about who is doing the naming. For most of the 20th century, the town was called Barrow on maps, after a nearby point named for a British Admiralty official who never went anywhere near it. In October of 2016, residents voted on whether to adopt the Inupiaq name, and on the 1st of December that year, Utqiagvik became official. The word refers to a place for gathering wild roots. The vote was close, and there were people on both sides with good reasons, and the older neighborhood down by the water is still called Barrow by people who live there, all of which is more interesting than a tidy story about renaming, because it's what an actual community argument looks like. And the practice at the center of that community is whaling. The Inupiat have hunted the bowhead whale along this coast for thousands of years. It is the most culturally significant harvest on the North Slope, and it's not a symbolic one. It is a substantial share of the food. The spring hunt goes out through leads in the sea ice in skin boats. The fall hunt goes out in aluminum boats when the water is open. In a good spring, something like 10 whales might be landed at Utqiagvik, and every one of them is divided by a system of shares that has rules. And those shares move through the community across the whole rest of the year, to the crews, to the captain's household, to elders, to feasts, to families who didn't hunt. Now consider what that requires physically. A landed bowhead is tons of meat, mactac, and blubber, arriving at once in April or in October, that has to be kept cold and dry until it's eaten, over months by hundreds of people, in a town where electricity is expensive and where a power outage in February is a real thing that happens. That is what the ice cellar is for. It's a logistics answer to a logistics problem, which is why losing a cellar is a practical emergency before it is a cultural one. When a cellar floods, a whaling crew loses its storage for the season, and the family that owns it has to find another answer, and the answers available are worse. Freezers cost money to buy and money to run, and they fail when the power fails. Storing that quantity of meat in sealed containers introduces a food safety risk that the open, cold, dry chamber did not have. And the taste is different. Meat aged in a cellar is what people want, and that preference has a technical basis. It's a processing method with a specific result, the same way dry aging a steak changes what you get. So the response has been what you'd expect from people dealing with a broken piece of critical infrastructure, which is to say practical, varied, and occasionally very clever. Some families have dug new cellars farther inland, away from the coast, trading the inconvenience of distance for ground that isn't going to be undercut by the sea in their children's lifetime. That's a straightforward relocation decision made at the household scale. And it's the kind of adaptation that never makes the news because nobody's suffering visibly while they do it. Some have gone the other way and brought machinery into a system that never needed any. Researchers and community members on the slope have considered and tested installing thermosiphons at cellars, the same passive heat pipes holding up the Trans-Alaska Pipeline, scaled down and put to work, chilling the ground around a family's food storage. Think about the loop that closes. A device developed to protect industrial infrastructure from thawing permafrost, repurposed to protect the oldest refrigeration technology on the continent from the same problem. Some cellars have been reinforced, shored up, relined. Some have been abandoned and their contents moved. The borough's public works crews have been sandbagging along the Chukchi shore to slow the water reaching the ones nearest the beach. A stopgap, and everyone involved knows it's a stopgap. But stopgaps buy seasons, and seasons matter. What gets least attention in all of this is the piece that deserves the most. Remember the finding from the monitoring program. The cellars that failed didn't fail purely because the ground crossed a temperature line. They failed from an interaction between warming and human activity. So what specifically is the human half of that? Some of it is obvious. Cellars are cut into ground beneath a town, and towns produce heat. Buildings leak warmth downward. Utility lines run warm. Vehicle traffic compacts snow, and compacted snow insulates differently than loose snow. Excavation and construction disturb the surface. But the mechanism the researchers laid out is more specific and much more interesting than generic warmth, and it runs through the road system. Roads in Utqiagvik, like roads everywhere on the North Slope, are built on thick gravel. The same insulating strategy as the Dalton Highway for the same reason. Over time, permafrost grows upward into the base of that thick gravel fill. That's a good thing structurally. It means the road has a frozen foundation. But it also means the road is now an impermeable, elevated barrier to water moving across the ground. Then add snow management. Snow gets cleared off the roads, which piles it into large banks along the edges. Snow fences around the community catch drifting snow deliberately, which produces big accumulations in their lee. Deep snow is an excellent insulator. That's why the tundra travel rules require it before heavy equipment can drive on the ground. So a thick snowbank sitting on the ground all winter keeps the ground beneath it from cooling down and refreezing the way bare tundra would. Come spring, all that piled snow melts at once, in a place where the ground beneath is frozen and cannot absorb it, and the road grades block it from running off. Water pools. And water, obeying the only rule it has, drains to the lowest available point. The lowest available point in a residential neighborhood in Utqiagvik is sometimes an open shaft going 20 feet down into the permafrost. That is how a cellar floods. Not because the Arctic warmed by some threshold amount on some particular afternoon, because a warming climate produced more meltwater and a less reliably refrozen ground, and because the town's own gravel roads and snowbanks, every one of them a sensible piece of engineering, built for good reasons, following the correct principle of protecting the permafrost, collectively redirected that water into the one hole in the neighborhood that had to stay dry. I find that humbling, and not in a hand-wringing way. It's a systems problem of the purest kind. Every individual decision was right. The road should be gravel. The snow should be cleared. The fence should catch drift. The cellar should be deep. Put them all in the same square mile and add a few degrees, and the assembly does something none of its parts were designed to do. The people who worked on that monitoring network were candid about a second failure too, their own. They wrote that for most of the program's history, information had flowed one direction. Scientists collected data and told the public about it. There wasn't much of a conversation, and over time, participation by cellar owners declined. Access got harder, permissions got complicated, loggers went missing, and by the last 3 years of the record, only 2 cellars were still reporting. Read that plainly, and it's a research program losing its data set because it hadn't built enough of a relationship to keep it. The authors said as much and proposed a different model built around community participation, one that starts by working out and communicating the actual chain of causes with the people who own the cellars, rather than handing them a temperature curve. I bring this up because it cuts against the reflex in stories like this one, where science arrives to explain a place to its residents. On the North Slope, that reflex gets the facts backward. The borough's own wildlife department has run bowhead whale censuses for decades. Work that helped overturn earlier scientific population estimates that were badly too low, and that is now cited internationally. Local hunters' descriptions of ice conditions, current patterns, and animal behavior are used as data because they are data, collected across more seasons and more miles than any research crews can manage. The expertise on this coast is not all imported. Quite a lot of it lives there, and always has. Which is the frame you need for the question people outside always ask, which is, why don't they move? It's asked innocently, and it lands badly. And the reason it lands badly is that it treats a place as a location rather than as a set of relationships to specific ground. But it also has a straightforward practical answer. And the practical answer is more interesting than the sentimental one. Move where? That's not rhetorical. Go inland from Utqiagvik, and you are on the same coastal plain, underlain by the same continuous permafrost, patterned by the same ice wedges, with the same active layer thawing a little deeper each decade. There is no nearby ground that is exempt. The physics that undermine a cellar on the beach are operating 100 miles inland too. They're just operating more slowly, without the ocean accelerating them. Go far enough inland to leave the permafrost behind, and you have left the whales. Bowhead whales migrate along this coast. They pass Point Hope, they pass Wainwright, they pass Utqiagvik, they pass Cross Island off Nuiqsut. Every coastal community on the slope is where it is because it is a good place to intercept animals that come by on a schedule. Move the town and you haven't relocated a settlement. You've ended a food system. There isn't a supermarket answer waiting at the other end of that decision. Not at Arctic freight prices. It's also worth saying that there is no single North Slope situation. The borough takes in 8 communities: Utqiagvik, Point Hope, Point Ley, Wainwright, Atkasuk, Nuiqsut, Kaktovik, and Anaktuvik Pass. Scattered across an enormous territory. They do not all face the same version of this. Anaktuvuk Pass sits inland, up in a valley of the Brooks Range, where the permafrost is thinner and the ocean is not a factor at all. Atkask is inland on the Mead River. Kaktovik is out on a barrier island at the eastern end of the coast, which puts it in an entirely different relationship with waves and ice than a mainland bluff site. Point Ley and Wainwright and Point Hope each sit on their own geometry of spit, lagoon, and exposure. So the North Slope permafrost problem is really a set of related problems with different shapes, and the useful conversations about them happen at the scale of a specific shoreline and a specific gravel pad, not at the scale of a region. And the practical calculus is worse than that, because relocation on permafrost is itself a permafrost engineering project. Every building you put down at the new site needs pilings or an insulated pad. Every road needs gravel, and gravel has to be mined and hauling on the North Slope happens inside that winter window that keeps getting less predictable. Airstrips, water, sewer, fuel storage, all of it, all engineered against a ground temperature that is moving. The cost of building a town properly on this ground is exactly why nobody builds towns on this ground casually. So the actual decisions being made are incremental, specific, and local. That's what adaptation looks like when it's real, rather than rhetorical. Shoreline protection, where the shoreline is the immediate problem. Cellars relocated inland one household at a time. Cellars fitted with heat pipes. Structures re-leveled. Snow management reconsidered, since the snowbanks turned out to be part of the mechanism. Hunting practice adjusted around ice conditions that no longer match what they were, which is a serious matter. The spring whaling hunt goes out onto shore-fast ice and works from its edge, and the thickness, stability, and duration of that ice is a safety question before it's anything else. Crews read that ice with a body of knowledge built over generations, and that knowledge is being applied to conditions it wasn't built on, in real time, by people who have every reason to get it right. None of that is picturesque. It's maintenance. On a coastline. Forever. Which is, when you think about it, exactly what the oil field is doing too, with more money and less at stake. Let me put one more number beside this because I think it reframes the whole question of who is exposed here. The bill for climate damage to Alaska's public infrastructure, that $5.5 billion figure over 8 decades, with permafrost thaw responsible for roughly 38% of it, is a state-level number. It covers roads and airports and buildings across a vast area. The North Slope's share of it is real, but it is not the largest share. What the North Slope has, that a road in the interior doesn't, is a set of assets that cannot be relocated at any price. A cellar can be redug inland. A whale migration route cannot be moved. A gravel pad can be rebuilt. A stretch of shore-fast ice that holds a crew safely in April either forms or it doesn't. That asymmetry is the thing I'd want someone to take away from the human part of this story. The industrial infrastructure on the slope is expensive and impressive, and it is, fundamentally, replaceable. You can spend more money and get more thermosiphons and re-level a module and reroute a road. The subsistence infrastructure is cheap, ancient, and irreplaceable, and it depends on physical conditions that money cannot manufacture. What struck me, working through all of this, is that the two systems are not in different categories of risk. They're in the same one. The pipeline supports at milepost 734, and the ice cellar behind a house in Utqiagvik failed for the same reason, which is that both of them were founded on ground, whose stability was treated as a constant, and both are now being kept in service by actively pumping heat out of that ground with sealed tubes full of ammonia. An oil company and a whaling captain using the same trick. There's one more group of people in this story who deserve a mention, and they're the reason we can say any of this with confidence. The permafrost temperature record for northern Alaska exists because for nearly 80 years, somebody has been going out to a set of holes in the ground and lowering a thermometer down them, once a year, every year, through cold, through budget cycles, through the shifting institutional interest of a country that mostly forgets the Arctic exists between news events. The Geological Survey's deep borehole work started in the late 1940s. The observatories along the pipeline corridor have been read every year since the mid-1980s. The thaw depth monitoring program has been measuring the active layer at fixed grids for decades by the least glamorous method imaginable, pushing a steel rod into the ground until it stops, and writing down how far it went, hundreds of times per site, every August. That is where the numbers in this story come from. A rod, a hole, a thermometer, a notebook, and a very long time. I have a lot of affection for that kind of work, partly because it's invisible, and partly because it's the only reason we can distinguish between what has actually happened and what somebody has asserted. When you can say that the ground at 65 feet down at a specific site on the North Slope has warmed at a measured rate per decade since the year 2000, you are standing on somebody's boots and somebody's August. And when you can say that the mean annual ground temperature at a research site near Deadhorse went from about 17.5 degrees Fahrenheit in 1988 to about 28.5 by the mid-2010s, that's not a projection about the future. That is a measurement of the past, taken by people who were there. The same is true, in a completely different register, of the cellars. 71 holes in the ground in one town, most of them dug before anybody was monitoring anything, each one a small vertical section through the top of the permafrost, maintained across generations by families who checked them several times a year because their food was in them. Nobody designed that as a scientific network, but it functioned as one, and it reported an anomaly early, and the reporting was accurate. That's the thing about a refrigerator made of ground. It doesn't have a warning light. It just stops being cold enough, and the person who opens it knows before anyone else does. So let's answer the question we started with, because it does have an answer, and the answer isn't a secret installation, or a buried anomaly, or anything that requires a conspiratorial tone to make interesting. The thing the North Slope holds that almost nobody talks about is the ground itself, not as scenery, as a structural member. Everything on that landscape, the oil field, the highway, the airstrips, the villages, the pipeline, the pads, the runways, the 136 exploratory wells drilled across the reserve in the middle of the last century and walked away from, was built on a single assumption that nobody wrote into a specification, because nobody thought it needed writing. The assumption was that permanently frozen ground would stay permanent, that whatever else happened, it would go on being a solid. That assumption held for the entire period during which the modern North Slope was constructed. It's holding, mostly right now. 2,000 feet of frozen ground under Prudhoe Bay is not going anywhere in anyone's lifetime. And I want to be clear about that, because a story that ends with the Arctic dissolving is wrong. And being wrong in that direction makes people stop listening. What's changed is the margin. The top 20 or 30 feet, the only part that actually holds anything up, has warmed measurably at a rate that has been recorded at fixed depths in fixed holes by the same institutions for decades. The active layer thaws deeper. The wedge tops go, the troughs deepen, and the water reorganizes. The coast, where warm seawater now has 3 months a year instead of 6 weeks to work at cliffs that are 80 to 90% ice, comes in at 56 feet a year in the worst places and takes another 12,000 tons of ancient organic material into the Beaufort Sea from a 5-mile stretch while it does. And the two things buried in that ground turn out to have almost nothing in common except their address. One is an enormous quantity of ancient carbon, 1,400 to 1,600 billion tons across the northern permafrost region, roughly twice what's in the atmosphere, most of it near the surface. Some fraction of it becomes available every year, at a rate the science can bound but cannot yet pin down. That last part is genuinely unresolved, not merely underreported. The other is us. 80 years of steel and diesel and casing and reserve pits and refrigerant piping installed by people who had no reason to doubt the foundation, being cataloged and plugged and hauled out now at $60 to $100 million for the last 6 holes by an agency that ranks its own priorities by how fast the coastline is moving. The clue was the cellar. The case is the ground. And the ground is doing something much harder to notice than drama. It is quietly withdrawing a condition that everything above it was designed around. Here's what that looks like on an ordinary day. It's August in Utqiagvik. The sun has been up continuously since May, and it will keep being up for a couple more weeks. The tundra is soft and wet and loud with birds. Out on the coast, the water is open, and somewhere along a low bluff 100 miles east, a notch is working its way back under a piece of ground that still looks perfectly solid from above and will drop into the sea sometime in the next few weeks, probably during a storm, probably at night, with nobody there. And in town, behind a house, somebody lifts a hatch in the floor of a shed and starts down a ladder. They're not taking a measurement. There's no logger down there anymore. They're going down because that's where the food is. And because you check on a cellar the way you check on anything you depend on. 20 feet down, in a room cut out of frozen ground by somebody's grandfather, they'll put a hand against a wall and feel whether it's hard or whether it's giving, and look at the floor for water that shouldn't be there, and know within about 4 seconds whether this year is going to be fine. That's the instrument. That's been the instrument for 1,000 years. It reported an anomaly decades before the satellites, and it was believed late, which is the part I'd want to leave you with. The cellar isn't a casualty in this story, it's the sensor. And what it has been detecting all along is an assumption, one that a town, an oil field, a highway, a pipeline, and a federal well plugging program all share, without ever having agreed on it, and that the ground has begun, very slowly and without any announcement, to stop honoring. If this is the kind of thing you want to know about the ground under other places, the assumptions holding up landscapes people drive across without a thought, hit the like button, because that's honestly how a thing like this ends up in front of people who'd care, and subscribe if this is the sort of ground you want to keep walking on. And I'd like to ask you something specific in the comments, because I think the answers will be better than the question. Somewhere near where you live, there is a piece of infrastructure that only works because of a physical condition nobody checks. A road built on ground that used to drain a certain way, a bridge sized for a river that used to run a certain volume, a basement, a seawall, a levee, a culvert, a tree line, a well. Something built by people who were completely reasonable, against a background they had every right to treat as fixed. Tell me what yours is. Name the place and name the assumption. I suspect there are far more of them than anybody would guess, because up on the North Slope, the assumption was that the ground would stay frozen. It was a good assumption. It was correct for about 10,000 years. And it's the kind of thing you only find out you were relying on when you climb down a ladder in August and put your hand on the wall.